Hello to all fans of physics and physical experiments. This is Alexei Kolchin with you, and today's video is dedicated to a phenomenon known as percolation. Translated from Latin, it simply means seepage. So imagine a vessel made of a porous material, and water is poured into this vessel. If there are enough pores, or they are large enough to connect with each other, then the water will find a path and seep through the walls of the vessel. But if there are few pores or they are too small, then no such path will be found. And it's clear that there is a certain boundary between these two cases. This video is dedicated to exploring that very boundary. Now I'm going to conduct a few experiments, not with water seeping through, but with electricity. For this, we've assembled the following setup. Here there's a plastic tube with a metal disc placed at the bottom and lead shot poured in from above. Now I place a metal piston on top of the lead and press down on it. The resistance of the circuit drops and the continuity tester goes off. Now I'm going to mix the lead shot with millet, whose grain size is roughly the same as the size of the pellets. And we'll see whether electric current will flow through such a mixture or not. Right now, half of the mixture's volume is lead and the other half is millet. And we tried to mix them as thoroughly as possible, although it's difficult because the pellets tend to sink to the bottom. And I press down on the plunger with great force, and we hear that there is contact. Percolation has occurred. We conducted 5 experiments with this mixture, and in all 5, electric current flowed through the mixture. This means that the probability of percolation for this mixture is quite high. Next, in order to determine the threshold concentration of lead, we need to increase the proportion of millet in the mixture. In this mixture, there is already 60% millet and 40% pellets. It takes more force to press down, but there is still contact, although the resistance of the mixture has become noticeably higher. And again, we conducted 5 tests, and in all of them, current flowed through the mixture. Let's continue increasing the proportion of millet. Now the mixture contains only 30% lead and 70% millet. Could there really still be electrical contact in this case? I'm pressing with all my might, and contact appears. Percolation occurred. We conducted 5 more tests, and in 4 of them, percolation happened, and only in 1 was there no electrical contact. We'll have to increase the proportion of millet to 80%. Now the multimeter is set to its maximum range of 200 megaohms. I'm pressing the piston with all my strength, but there's no contact. Then the result was negative in all 5 previous tests. We conducted 5 more tests with the mixture that contained 25% lead and 75% millet. And not once did percolation occur in these tests. This means that the conductivity threshold lies somewhere in the narrow range between 25 and 30% lead content. And we can't advance further with the experiment here, because we have difficulties achieving a uniform mixture of lead and millet. But in any case, this narrowness of the percolation threshold needs to be explained somehow. But before we move on to the explanation, I want to show you a few computer models of percolation that you can also play around with. The links will be provided, and the first model is set up like this. In it, water or spilled oil flows downward. There are cells in one horizontal row and cells in the next row shifted diagonally. And the flow can occur diagonally to the right and diagonally to the left. Then beneath this row is the next row, then the next, and so on. And these cells can randomly be filled, blocked with a certain probability and then nothing can flow through them. Or they can be unfilled, open, and then flow is possible through them. And in the model, we can change this probability of the cells being filled. Now let's see what this leads to. And I'll start with a cell filling probability of 60%. We set it up and start it. And you can see that only one branch remains. It keeps going, and then it dies out. Let's try again. Starting it. And the flow dries up. Oops! Come on, more! It didn't make it. On the other hand, if I set the probability to 65%, set it and started it, you can see that the percolating flow is quite abundant. It goes lower and lower, so I have to launch the next screen. It seems like everything almost died out, but then suddenly it spreads again across almost the entire width of the working screen. Now there's a branch left on this side. It keeps going and going. And I'm not sure we'll live to see this flow dry up, although of course at some row there is a chance that all the cells will be killed and the flow won't go any further. But that probability is extremely low. So we'll pause this experiment. Let's take a look at 63% now. Set it up and off we go. Well, here the outflow happens faster.
Nevertheless, one of the streams has seeped onto the next screen. And it looks like it will reach the next one as well. We wait. It has reached the third screen. It doesn't expand or contract, it just exists. Now it's already on the fourth screen. But it seems like it's time for me to pause this experiment. And you can play around with this program more carefully. Oops, everything just stopped. For me, on the fifth screen. You can more carefully figure out how and in what way this seepage occurs. In another model, the plane is divided into cells. And some of these cells are open while others are closed, again randomly with a certain probability. And water can flow from already filled cells into their neighboring cells along the sides if those cells are open, and from those cells further and further. So the fill density is 56%. The spread starts from the center, but it fades out somewhere, once again. And again we see that percolation stops somewhere, only occupying a certain area of the square. Let's set it to 60% and see what happens. In this case, set it, started it, and percolation occurred across almost the entire square. One more time. Oh, how interesting. Now a fractal grows in that direction and still fills a significant portion of the square. Let's do it once more. And again, the square is filled from one side to the other. Well, now let's set it to 50. 8. The intervals between them. Ready? The fractal grows again, quite large, but as we can see, the filling happens to a lesser extent, this time, one last time. I recommend you try playing with this program yourself. And finally, here's another computer model in which the walls between the square cells will be destroyed. Now, 30% of the walls between the cells have been destroyed. We can see that. All the clusters are very small. Here you can move the slider, and everything will be redrawn. 33%, 37%, 39%. The clusters are gradually growing. 42, 43, 46, 49. Look how big they've become. And 50. Here, we'll click around a bit to refresh the image. We can see that a typical cluster now stretches from wall to wall. And at 49%, well, let's try 48. Well, that can also happen sometimes. But the other clusters, while not as large, are still quite sizable. Now, if I go above 50, 51, all the other clusters become small. 52. I'm clicking. There's one large cluster and some tiny ones. Let's set it to 55. The small ones have become really tiny. And if I go up to 60, only these tiny, tiny cells remain. So the threshold is somewhere around 50%, okay, of the walls between the cells being destroyed.
Andre, of course, it's wonderful that computer models free us from the difficulties we encounter in real-life experiments. But I have a question. So we've set the engine in a certain position, but when we repeat our trials over and over, the models, generally speaking, give different results, and we still can't precisely determine the threshold at which percolation occurs.
You know, that's a good question. And I think we'll talk about it a bit later. But right now I want to say that I know of one model where this threshold is determined very simply, and that's the game of hex. Now I'll show you how it's done. This game is played by two people on a board made up of adjacent hexagonal cells. They take turns placing X's and O's in these cells, and each player wants to connect their sides of the board with a path. The winner is the player who manages to do this. And look, if the first player builds such a path, then they've blocked the way for the second player, and the second player will no longer be able to build such a path. Now let's imagine that exactly half of the spaces are randomly filled with X's, Itza, and the other half with O's. If O's don't have a path, that means the X's have blocked their way, which means the X's have a path. It turns out that such a path always exists, either for the X's or for the O's. And it's clear that in a symmetric situation, the chances for X's and O's to have the path are exactly 50% each. And that means this is the percolation threshold.
Andre, so you're saying that 50% is exactly the percolation threshold. But it's obvious that if we take, say, 45% X's instead of 50, we'll still occasionally get paths made up of X's rather than O's. In what sense is 50% the threshold?
You see, it's important to ask with what probability these paths will appear. And when our field is small, these paths will probably appear quite often. But you have to imagine that we take these small fields and connect them to each other, assembling a very large field. And now we need to ask, what will happen on such huge fields? If we take not 50%, but say 48 or 49, I suspect that this will depend on the size of the field.
Well, that means we need to sort of take the limit as the size approaches infinity in some sense.
Right, extremely large. I think we'll look for something now.
Compared to the size of a cell.
Yes. We'll look for something interesting now, and we'll definitely find it. This material is taken from the channel of Niels Berglund, a specialist in computer modeling of stochastic processes. Percolation is happening on a hexagonal lattice from the left wall, and in the small window, the percentage of filled cells is shown. Right now it's at 40%, and it seems like percolation is still a long way off. But the size of the clusters being joined is growing rapidly. 47, 48, 49, and at 50%, a single large cluster appears from wall to wall. Percolation happened almost instantly. After that, this cluster fills an increasingly larger share of the cells. Now I want to explain how I, although not in a strict sense, nevertheless understand the experiment that Alexei showed us at the beginning of this video. We know that for the uotio mixture of millet and lead pellets, percolation began when the number of pellets made up 30% of the total number of these spheres. But this means that if I have, say, about 1,000 spheres lying on the surface at the top, then 300 of them are pellets and 700 are millet grains. And these 300 pellets in some way form chains that grow down to the bottom surface. And of course, it's not just a single on the chain of pellets that would be easy to break. No, by this point it's already a sprawling cluster. And many of these pellets that are on top and provide conductivity down to the bottom are also interconnected. I think that's true for a significant portion of them. Now, let's imagine that I place another identical cylinder on top of this one, which also has 300 lead pellets reaching down to the bottom. And again, a significant portion of them are interconnected and extend all the way to the top. And in order to connect the very bottom to the very top, all I need is for just a single pellet from the lower cluster, which extends to the bottom, to come into contact with the upper cluster, which extends to the top. And it's clear that the probability of such an event is quite high in this situation. But this means that if the bottom of the cylinder was already able to conduct, and the top was also able to conduct, then the entire cylinder as a whole will conduct as well. In other words, as soon as we cross the threshold even slightly, the entire cylinder as a whole will conduct. Well, then I will repeat the same reasoning, extending the cylinder upward, increasing the size of this sample. And it seems that this isn't rigorous, of course. I'm using the word seems again. But it seems that nothing will change because of this. This is how I, at least in some way, perceive and imagine this percolation threshold.
While Andre was explaining why the percolation threshold arises, I discovered something on Niels Berglund's channel that closely resembles what we did in our physical experiment. It's a cube with sides of 32 units. The proportion of its conducting cells gradually increases and percolation occurs when this proportion reaches 32%. And in our experiment with round grains, where the contact between neighboring pellets was of course worse, but the packing could be denser, the percolation threshold was around 30%. It seems to me that we achieved excellent agreement between the physical experiment and the computer simulation.
Alexei, aren't you surprised by such good agreement between the computer simulation and the experiment you showed? After all, lead pellets are much heavier than millet grains. And obviously it's just impossible to mix the pellets and millet evenly.
Well, first of all, it is possible, but we didn't have a special setup for that. Secondly, the two of us tried to mix it together and the separation into millet and pellets happened right in the teaspoon from which you were pouring the mixture. But nevertheless, our experiment matched the results of the numerical simulation. And this means that the percolation threshold is so sharp that even our experimental errors couldn't prevent us from determining it.
You know, that's really amazing, because the threshold turned out to be very clearly defined. And in my opinion, we should also talk about what mathematicians do and what kind of percolation theory they develop. As for mathematicians, here's what can be said. They study specific lattices, quote, with various types of symmetry, for example, square or hexagonal lattices. At the same time, they investigate the properties of infinitely large clusters that emerge on these lattices when the percolation threshold is reached. The boundary of such a cluster is a closed curve without self-intersections, which can be described in terms of random walks. This curve possesses the property of fractality, and it has the same structure at different scales. An essential property of fractals
is their fractal dimension, which we will discuss in detail in one of the upcoming videos. This dimension is determined by the type of lattice, and it turns out that it remains unchanged under any conformal transformations of the plane. The study of such transformations was undertaken by the remarkable St. Petersburg mathematician Stanislav Smirnov. For his work, in which he managed to find the percolation threshold values for certain types of planar lattices, he was awarded the Fields Medal in 2010, which is the equivalent of the Nobel Prize for mathematicians. But when it comes to three-dimensional problems, results so far have only been achieved through stochastic computer modeling. And developing a theory for this remains a task for mathematicians of the future, if it is even possible at all. And now our video has come to an end. For those who watched until the end and are of the right age, you are welcome to apply to the physics and mechanics and mathematics departments of Novosibirsk State University. And thank you all for your attention.